Yeah, so let's turn this on. So I've got some new material from the family emails, and one of the jokes was, my mind is like a browser with 13 tabs open. 3 are frozen, and I don't know where the music's coming from. I hear y'all talking a lot about inorganic. You have a test coming up? Today? Okay, yeah.
So we went to your CHEM YouTube channel to rewatch the symmetry videos.
Oh, really? Oh, good. I'm glad it's on there for you. Yeah. And that's why I put them on YouTube, because you can't get back to the Blackboard, version of those. So, yeah. So it's kind of nice. Yeah. So whenever you're there, if you're watching a video, leave a comment. Like say, hey, just, shout out. So like, hey, somebody, because I get all those comments. It's nice, Yeah. Find a mistake, say, I don't know about this. Yeah, let me know. I'll interact with you. Yeah, there's lots of comments on some of them. A lot of folks, there's a bunch of comments for a while there for this. So in India, they must have been having some kind of exam, like big chemistry exam, qualifying exam or something. And I got all these questions. It was on the intro video of Pekin Wanted to Buy the Book. And they were like, what book do you recommend for the MP1 exam or something like that? And I was like, I have no idea what you're talking about. So we have different systems, and so I have no idea what that exam was. But there was a lot of people. I got like 4 or 5 comments on it, different people asking about that. I was like, oh no. So today we're going to talk about statistical process control and control charting. So we're doing the control charting exercise. You probably should have around 15 data points now, getting close to it. And so it's time to generate your control charts, and so we'll talk about those things today. So anytime you want to monitor a process, you need this thing called the process control variable. Now, if you think about, I keep using sort of GCMS as our example. Think about all the different kinds of things that you could use to monitor on a system that's that complex. You could monitor the flow rate of the gas. You could monitor the temperature of the inlet, the temperature of the oven, although it's typically programmed, so that's kind of a complex variable. You could monitor the ultimate pressure on your vacuum if it's a mass spec, and you could monitor the electrical voltage on the if you've got an electron impact detector or something like that. So you've got all kinds of variables that you can monitor. A lot of times you use a control sample that you'll run through. So that sort of tests everything. If the sample comes out at the exact same time, plus or minus a small amount, everything else is probably behaving. So you need to find that one key variable that you can follow. And so it's a single measurement unit, and it indicates the performance of the equipment and the process. Because you eventually get too much data to keep in your head. There's just too many factors in a complex system. Or just think about your lab. What variable could tell you if the people, the processes, and the equipment and the raw materials are all what you expect. Okay, and so that's a real thing to think about in any kind of process control, is what is your key process variable, and so this variable should be unchanging if the process is unchanging. So it should truck along, same value. This means it should not change except for random fluctuations. So if it does change, something non-random happened, and it's time to investigate. So this key process variable is something that you look at, and it provides a sign, like a status sign that says good or investigate. And so as long as it's in the good range, you're going to cruise along, and then when it jumps out of range, then you go and take action. Notice how that's a pull process. And today we're going to talk about push versus pull in process control. So a push process is when I give you a schedule and say, you do this every day or every morning or once a week or once a month. I'm pushing you to do it. You don't need any data for that. And this is a pull process. You're going along, all of a sudden something happens and it pulls action out of you. Okay. And so that's what we're doing for the control chart. We've gone through, given you the approvals for your various data. You've been collecting that. Like I said, we want things that are going to be remain roughly the same, plus or minus random fluctuations. And so, like for temperature, a lot of people do temperatures, and so we always want to do today minus yesterday, so that essentially we have some positive numbers, some negative numbers. It should be, trending around zero. Maybe there's a little bit of an offset. Weight is typically bad, but daily change is good. Gas prices also, they don't have enough decimal places typically, but maybe if you have like a nationwide average, you get a third decimal place, and that might work. Okay. And so we've gone through and we've looked at the different data points. A lot of people are doing stocks. Step count fluctuates like crazy, but it is pretty random. and if it's not random, then you know what you did. Like had a person that would count their steps, they would time themselves walking from their parking place to the chemistry building, and of course they parked in the same place every day, Bowers or whatever, and so it was plus or minus, and it was pretty random. And then all of a sudden it was way out of control. So I looked at the control chart and looked at their action log, and I was like, oh, okay, so there was some event and that parking lot was blocked off and everything, and so then they had to park someplace else. And so again, a non-random occurrence. You could see it in the data, then you can do research on it and see what happened. So daily changes are good. There's some sort of random daily fluctuation in the process that produces these data. And then whenever that daily difference is more than 2 sigmas away from the normal behavior or the mean, something significant has happened in the process. And I've always seen that to be the case. Whenever people are tracking, like I said, step count or time doing a particular task, or screen time, or even had a student that was counting how many mouse clicks they play in a game. It was a video game. I was like, what? And it was like in the thousands of range. It was 10,000, 20,000, 60,000. And I was like, this was a shooter, they're just, and so it was pretty funny. Yeah, she was really excited about that. I was like, yeah, you go for it, because that sounds like it's going to be interesting data. And it was, but, it was rocking along, nothing but random variation and pretty wide error bars. But then all of a sudden, she's like, yeah, we went on this big mission, and, I clicked a bunch. So it was pretty interesting. So let's talk about the philosophy of this control chart. Okay, this is sort of been popularized now. This phrase, or this term Kanban. It's a Japanese term which means billboard or sign, and so it's something that's going to alert you to the action, or really give you the status of the system, like how's it operating. And you can go on. I just Googled Kanban to see in like past 5-6 years. There really wasn't much 5 years ago. Now there's just hundreds and hundreds of examples. And now they're really using it more like a billboard with little Post-its and so on. So you can make up sort of, if you're in charge of a process, a Kanban board, which tells you like in prep, actually being worked on and then finished. And you move the little Post-it notes from spot to spot. And at any given time, you can look at it and you can see how many processes are being prepped, how many processes are being worked right now, how many processes have been finished. And so it's a single glance, you can see the whole process. Okay. A lot of times these are called dashboards. And so you'll have a process dashboard, and you go and you look and see what the process dashboard is. We had to do this for our bosses. If we were managing any project, we had to have a 4-panel dashboard. We had to have expenditures versus budget. That was one panel. There was 4 panels. And so they wanted to see that your expenditures and your budget were right on line. If it was like this, where your expenditures were higher than your budget, they were like, what's going on? They say, well, the budget's linear by month, but we have a big capital purchase. And so there's not going to be anything, and then there's going to be a big capital purchase, and then nothing for a while. And so then we'll hit our budget in 3 months, because we spent like 5 months worth of money at one time, because that's... So a nice linear budget may not be reality. It may be a few consumables, a few labor costs, then a big capital purchase, and then consumables and labor costs, and then they meet back up at the end of the year. But that tells the boss immediately when they see that, whoa, I got to ask a question, because that's not what I was expecting. So the little budget panel was one. There was a process like a progress panel. Here's all your tasks. and which tasks are done, and they wanted to see that you were working on the tasks at the appropriate months that you were doing, if there were any problems. I'm trying to think of the third panel. The fourth panel was like alerts that the boss should know about. Like, is there something going on that with your project that's putting it in jeopardy? It might be on budget. It might be the tasks are going along, but that in the fourth month, the thing that you're going to have to do is that process is broken, and you're going to have trouble there. So there's a little alert box that says, hey, you need to help me out with this because I need somebody else's help on this, and you need to talk to other managers or whatever. So that's a dashboard, that's a Kanban, that's a billboard that tells you about the process. So a control chart is one of those. So calibration checks are often used in industry. And so what is a calibration check? Well, if you've got your calibration model, you put in your external standards or internal standards, and you've calibrated your equipment, then you can run a known concentration to check that calibration curve. And if it comes in on the line, you're good. You can keep going. The calibration is still good. And so that's what we mean by calibration checks. And if we say you're going to calibrate, say, every Monday for the week's worth of work, and then do a calibration check on Tuesday, Wednesday, Thursday, or whatever, or maybe you just do a calibration check once a week, that's, again, it's on a schedule, so it's a push. You're not looking at any data to make that decision. In fact, there's no decision to make. It's a push because it's a schedule. Okay. So every day or week, regardless of need. This increases costs potentially by calibrating unnecessarily. So I think that's the big key right there. What if that calibration was still good from a week ago? If your calibration checks hit the line, then it's still good. What might you do if you have a good calibration and the instrument's working fine, and then you recalibrate it? What have you done? You've introduced potential uncertainty. Maybe this week's technique in pipetting was worse than last week's technique. Maybe you're a little tired from the weekend and you do a poorer job. So you've actually ruined a really sweet calibration. So by calibrating or doing action on a schedule, sometimes you're introducing uncertainty when you think you're taking it out. Okay. So we could also miss a problem that occurs between scheduled calibrations. Because a schedule doesn't use performance tracking. If you go, and I don't know that they would do this, but let's say you calibrate on Monday and then you just analyze data Tuesday, Wednesday, Thursday. If you don't do any calibration checks in between, say you do one on Thursday and it's out, it's off the line. Well, was Wednesday off the line and you didn't know? Was Tuesday off the line? You didn't know. So now all of the data back to that calibration is suspect. So you have to redo the data analysis on Tuesday and redo the analysis from Wednesday. So it goes back to the last time you did a cal check. And so since that's uncertain, you need to redo it. So that's a lot of wasted time. The other way is to use a control chart, which operates on a pull philosophy. So we will calibrate when our system tells us it's needed. So do you see the pull, that telling you, that signal that tells you action is needed? That's called a pull. We use this all over the place. Anytime you go to the store and they're beeping the barcodes, okay, the store and the computer in the store is supposed to know what their inventory is. Okay, and so they know how many, frosted flakes they have, and you buy some frosted flakes, and that's the last box. And they probably make the order when there's 5 left or something. They program the computer. So when you buy the 5th to last box, beep, then the computer pulls an order. So the computer is making the order for the HEB, not a person. And used to, they'd go down and count the shelves. And they say, okay, we're getting low on frosted flakes. And they would make up an order. And that would take a person's whole time to make those orders. Now it's all automated. The computer's pulling the orders and so on. So we see that. We see how that works. This saves money by focusing on the problem and not the schedule. You don't want to buy frosted flakes on a schedule, trying to predict, how many frosted flakes the people in Huntsville are going to eat, because your schedule through July and August is going to be pretty low, and so you're not going to be ordering enough, and then all of a sudden school starts and you got a lot of college students who love Frosted Flakes, and they're out immediately. So let's look at this. This improves quality because the performance is frequently monitored, and I think that's the key. You're monitoring how the system is behaving. You can even do this throughout the day. Like you could do a cal check, since it's just one more sample. You could do that every 2 hours so that you don't have to, like if you cal in the morning and you go all the way until Tuesday morning, what about the afternoon? It's warmer, maybe the lab's a slightly different temperature, maybe you do a cal check after lunch. Okay, just one more sample, but and then you can test, you can say morning, you can control chart morning and afternoon, and see how that looks. So let's look at Top Hat. So I just really want to try to get you to internalize this idea of the pull. So what's the pull or Kanban or sign in our fire safety system? So these are various parts of our fire safety system here at the university. Okay, make your choice. One more. Three, two, one. Okay, moving on. Okay, so the fire alarm sound, very good. Why do you think that? So 15 people answered. Why do you think that's the case? It is the thing that makes you take action, and they've gotten better actually, because in the old days, the fire alarm, you could ignore it. It would go off, and you're like, I don't smell anything. Right? It was annoying, but it wasn't that bad, and you just keep working and they'll call all clear and come back and you'll continue to get some work done, right? That's the old days, okay? Now they've made them so loud, it's so uncomfortable to stay in the building that it drives you out. I mean, it forces you to take action. And so, yeah, that sound is the sign that you got to take action and leave. Now, notice it doesn't fix the system. Your action fixes the system. Part of the action is computer generated. It causes these little cups to pop out, and then it sprays water in the room. So we have the sprinkler system here too. And they have the fire loop, you have the fire department, you have the police policies for the fire drills and so on. So yeah, it's the sound that's the actual Kanban or sign that there's a problem. Okay, good. Okay, so let's talk now. We can do control charts in Excel, which is what y'all are going to do, but I want to just show you some of the tools in Minitab. Once again, Minitab has an automated control chart tool. You can just add your data and then update the chart. Add your data, update the chart. So you don't have to go in and type in formulas and copy formulas down and so on. So there's all kinds of programs out there that can help you with this. And so if you go under Stat Control Charts, variables for individuals, then you get this dialog box and you just drag the variable that you want to chart out here. So I've got like pipette volume here. So this is an example of checking a pipette volume daily to make sure that nothing's happened with your pipettes, right? What could happen with a pipette? Well, you could leave for the day. You never know if somebody comes in after you and is messing around with it, playing around with it. Pipette something and then turns it upside down, and then liquid gets up into the little baffle. And if there's liquid in the baffle, that reduces the volume of the baffle, which means it reduces the volume that it's going to pull and push. So things could happen. It could get dropped, and crack or something. So then you put in your tracking variable. You could put in the X value and give it a date stamp. So I have a date stamp there. Then you can set up your options for the mean and standard deviation. It'll calculate the mean and standard deviation. Or if you do the training period, like if you get the training period, you can type in the training period mean and the training period standard deviation. Then you have this little limits. You can pick watch limits and action limits. And so this one is using the sample standard deviation times the t-value divided by the square root of n. And then you have these little tests. So these are the tests for the data being in control. So here, let's just kind of walk through some of these. Like this one, this is telling you when to take action. So if you have 1 point greater than k standard deviations, and so this column over here is k. So for this test, k is 1. And so this is saying 1 point greater than 1 standard deviation from the center line. Well, that's pretty lax. I mean, it's 40% of your data almost is going to be outside of 1 standard deviation. So you might put a 2 there. You could put 1.96 for a 95% confidence. So only 5% of the time would it be outside 1.96 of standard deviations. So that's one we're familiar with, and that's the one we're using in our control charts. We're using a plus or minus 2 standard deviations. So it's a little more stringent than 95% confident. Okay. And then here, k points in a row on the same side of the center line. That's a trend, right? If you're going along and you have, all right, it says k points on one side of the center line. Well, that should be a large number, right? So they picked 9 here. This was the default for Minitab. So it's saying you're collecting data, but all of a sudden you have a run of 9 on one side. What's the probability of getting 9 on one side? First of all, let's just say one point on one side. So if the data is centered on the mean, if it's not skewed, what's the probability of being high or low? Yeah, 50-50, right? High or low. It could be one side or the other. And so this is 9 times on one side. So it's 50-50, 50% or 0.5 to the 9th power. That's the probability of getting 9 points in a row on one side. Okay. It's a pretty low probability. And so then you might be out of control if something's happening, okay, like that. If they're all increasing or decreasing, then you've got a trend, right? And so here's 6 points in a row, all increasing, or 6 points in a row, all decreasing. K points in a row, alternating up and down. So if you have 14 points in a row, up, down, up, down, up, down, for 14 points, that's not random. And so you can turn, any one of these things that may alert you to being out of control. Now, what could cause this one? This is a strange pattern. That I would turn that one on if I was doing cal checks in the morning and afternoon, before and after lunch, because that would tell me if there was a significant difference between morning and afternoons, right? Up, down, up, down, up, down, 14 times in a row. I say, okay, my morning and afternoons, even though there may not be 1 or 2 standard deviations away from each other, they're alternating. I have detectable difference. It may not be significant, but it's detectable difference between morning and afternoon. And so that's one. So you kind of need to know your process, or think about your process and which test you're going to use to determine if you need to take action or not. And so these are sort of action level tests. You're going to take action and explore your data more when you have when one of these tests kick in. So let's look at some of these others. K out of k plus 1 points greater than 2 standard deviations from the center line. So this is saying 2 out of 3 points that are greater than 2 standard deviations above the center line on the same side. So that's a little more stringent test. You have to have 2 out of the 3 points that are greater than 2 standard deviations away. K out of k plus 1 points greater than 1 standard deviation. So this would be 4 out of 5 points greater than 1 standard deviation away. Then you have K points in a row within one standard deviation of the center line. So now this one's strange. This is 15 data points within plus or minus one standard deviation. That sounds like a good thing, doesn't it? Because you've got the random spread of data, and now all of a sudden your data's tightened down, and it's all within one standard deviation for 15 consecutive data points. Why would that want you to look at the data? Why would that cause you to look at the data? What is it telling you, maybe? You know, we have the mean value. We also have the standard deviation value. So in our training set, we look at our data and we get the mean and the standard deviation. Now, when the data is all increasing on one side or decreasing on one side, that's telling us our mean is shifting. Okay? But when the data is really widely variable and now it pinches down, that's telling us that our standard deviation is shifting. It could shift too. And so we have our training data and all of a sudden the variability shrinks. Okay. Like think about doing your steps. You have random behaviors day in and day out, and then you start going to the gym. And every day you start walking around the track, for a quarter mile. Then you've reduced your variability. You're going to not have these days with no steps, okay? And you're going to be tired, so you're not going to step a whole lot more after you get home. You've done your walking. And so your standard deviation has changed. So this particular test would catch that. It would catch that when you're something significant has changed in your data. A significant change could be the mean, but it could also be the standard deviation. Okay. And then the last one, K points in a row greater than one standard deviation from the center line. So 8 points in a row outside the standard deviation. So once again, that could be your standard deviation changing, but it's getting wider, not narrower. So. Now what you don't want to do is to turn all of these tests on, okay? If you turn all of those tests on, you're going to be chasing every data point is probably going to have a flag on it. And you're going to think that your data is never in control. You want to only turn in those tests that are significant for your process. And so that takes a little bit of experience. Okay. So here's that control chart of volume. We've done the training period already. That's where the mean and standard deviation came from. And notice this one is inside the limit, but it's colored red, which means it's indicating something that's out of control, and there's a number 7 by it. And then here's some red ones that have number 1s by it. And so these little numbers that it puts on here, it is explained in the session log. So this is the session log. Minitab has this session log, which is really good for forensics, because if you're in Excel and you change the formula, there's no record of what the old formula was. There's no record of when you changed to the new formula. You could screw up your spreadsheets and there's no record of it. Whereas in Minitab, everything you do to the data, there's a log about it. And so you can go back and track to say when you made that control chart. If you change the limits, it'll say when you regenerated the control chart and changed the limits. And it has the old limits and it has the new limits. And so you have records of everything you do. That sounds daunting, right? But it's really a good protection. When they accuse you of manipulating the data, you can say, here's my session log. You can see that I took action when the data required it, not because I wanted a particular outcome. Okay. And so here's, again, more than one. So the test number 1, more than one standard deviation outside the center line. It failed at data points 17 and 18. So that's that test number 1. And then test number 7, 15 points within one standard deviation of the center line. And so I said invalid for this process. I don't know that it's. See, all of these 15 data points within one standard deviation of the center line. And so, so it flagged it. Okay. So you just want to make sure that your tests, your statistical tests that pull action are valid. Because if they're not valid, then you're getting pulled into action unnecessarily. Okay. So these control charts really do help ensure valid results. This is what your control chart's going to look like. And it should be formatted just like this, with the red line, the orange line, the green line, even those colors, no markers on any of the action lines or the mean, markers on the data. And I told you in PChem, and I tell you again now, don't ever draw a line on a chart unless you know the equation for that line. And most of the time, we don't connect our data points, but these data points are kind of crammed together. And so for clarity, you can connect the data points as long as you connect them with a straight line. Because every line on here, I know the equation for. I've got 2 data points here and a line in between. And those 2 data points, I could come up with the formula for that line. So not that you would ever need to figure out what this point was halfway between those 2 data points, but you have the line there and you could come up with the formula and you could figure it out. Okay. What I really am opposed to is the smooth lines, where it's taking a smooth line through the data. And occasionally people they're not paying attention when they build the chart in Excel. And instead of the sharp lines, they do the smooth lines. And it draws what's called a spline. And so it doesn't have any of these sharp points. It kind of curves it around like that through to every data point. And that's, again, you don't know the equation for that spline. And so you're drawing a line on your chart and you don't know the equation for it. So it's just a risky situation for you presenting data, and someone asks the question, well, can you calculate this data point right there? You've got a line and you can't because you don't know the equation for that line. So you've drawn something on there that you can't defend. And you can say in the figure caption that the lines drawn between the data points are there for clarity. Okay, they're not meant to be a model. So then also, you plot 2 different data series. One data series will be the training set, the first 15 data points. That data set, the training period, is what gives you the mean and standard deviations. And then you use that same mean and standard deviations for all of the other data. So you don't change it each day or each week. It's fixed. After the first 15 days, that mean and standard deviation are fixed. And then you see if the data stays in control. So every data point beyond the action limit must trigger an action. And our action that we're going to do is make a log entry, because we can't go correct whatever it is that we're studying. We're not going to change the temperature of Huntsville on a daily basis or whatever. Gas prices, I don't know. We're not going to stock. How are you going to change Disney stock to correct it? But anyway, we'll take an action because that's what you would do in real life, except our action will just be to make a log entry. Okay, so here's how we set up our spreadsheet. We have that training period, and notice that the mean, the average, only contains those data points. It does not go down below that. So like here I have some data for 16th, 17th, and 18th days, but I'm just calculating the mean based on the first 15 days. That's why it's called the training set. What are we training? We're training ourselves as to how we understand the data. So it's not really, I don't know why they call it a training period, but it's training your model, I guess. So there's our mean, and then the standard deviation, same thing. We've got 15 data points. I guess we could use the population or the sample. It doesn't really matter at that point when you have 15. So you pick the standard deviation for the data set. And then you calculate your limits. So we have, this column is just the mean, all the way down, same data point, all the way down. Now, there's probably neater ways to make the spreadsheet, okay? And that's fine if you want to do it some different way, but this is the easiest, I think. You just copy that mean value down to every column. So there's just the same number in every column. Then you have the mean plus 1 standard deviation. So that is this value plus the standard deviation equals that. And then you have that mean value minus the standard deviation. And then you have the mean value plus 2 times the standard deviation. And then you have the mean value minus 2 times the standard deviation. And those formulas are calculated. Everything's anchored so that you calculate it down, you get the same value. And so then you can plot those columns and not show the markers. Just do the lines. Now, this alert column, I would like for you to use these Boolean operators, the if-then statement in Excel. Here's kind of how the if-then statement is constructed. It's got 3 fields, right? You have if and then open and close parentheses. Inside the parentheses, these are the arguments. The first one is the condition, okay? So you need some sort of logical condition, like is this number greater than that number, okay? And then a comma. And then you do this piece if it's true, and you do the next piece if it's false. So it's just a simple thing, true, false. If this is true, do the first comma field. If it's not true, do the second comma field. Very simple. In programming, it would be if, then, else. So if you have a conditional, then sets up the first action if it's true, else. Else means if it's not true. Okay. And so I have this first one, which is kind of complicated. I have an OR function. And so an OR says, if this is true or that is true, return true. Okay. And so then the true action is beyond action level. The false action is do nothing. Okay, so two quotes with nothing in between them will just produce a blank cell. So that's kind of nice to know. And that's how you get it to just put nothing in that cell. There's a formula there, but it produces nothing. If it's neither high nor low. If it's inside the limits, don't show anything. So you have a lot of blanks, and then you have an alert. Now this is good, but I think this is better to go ahead and do 2 nested if-then statements. And so I test the high condition first, so then I can say above action level. So if it's higher, if D8 is higher than H8, what's D8? That's my data. So the data point, if it's higher than my upper action limit, H8, then report above action level. Else, so if it's not above, then I do another if to see if it's below. If D8 is less than I8, which is my low action limit, then I return below action level or nothing. So I won't get to this nothing unless I wasn't high and I wasn't low. Okay, so it went through both filters and ends up with producing nothing. If I'm not high and I'm not low, then it produces nothing. Okay, and so that's a little better equation. So hopefully you use that one. It's just kind of nice to see it in your alerts. Oh, we're high. Oh, we're low. Okay. So every data point beyond the action limit must trigger an action, and that action is to make a log entry. To do a little research if you're tracking stocks or something, or if you're tracking something with your own behavior like screen time or steps, then you can think about the day that was out of control and provide some input. Okay, so then this alert log, that's why it's nice to have something that's researchable. If you're doing stocks, you can get on Google Finance and try to see what happened. It's always market uncertainty based on some statement of some politician, but sometimes it's significant. Like when we were tracking the Yamaha stock and we had a tsunami that hit Japan and a nuclear meltdown and an exploding nuclear power plant. Those were some significant events, and so it's pretty easy to do research on those. Other times it may be difficult to find, but whenever you do your research, if you would, put your source, okay? Even if it's the same source, maybe you could put an asterisk. Like if you're doing weather, you can say all of my weather sources came from this website. But if you find a particular article or something, go ahead and put the URL in your alert log down here. So it says comment on probable cause. Cold front came through, and you could say weather.com or wherever you got your data. Maybe a link to the data. Okay, and so now this is your properly formatted control chart with that training period in green. It's sort of really, this is the one that I want you to look at. So this one here, use that as your example. Notice how the days are sideways. Now I don't like this date colliding with the thing, so I would move the chart up just a little bit so we don't have this. I'm going to be looking at this with a fine-tooth comb because there's not a lot of writing associated with this assignment. Okay, so I'm looking at every little thing. Notice it doesn't have a box around the outside of it. That's called a bounding box here. and Excel puts it in there by default, and I take off for that. We don't need it, okay? So it's that outside box boundary that I don't want to see. This one I want to see. So sometimes I'll tell people no bounding box, and then they'll eliminate this one too. And I'm like, no, that's the chart. So leave the box around the chart. Don't put an extra box around the outside of the figure. Okay. Label all of your legends. I don't want to see like series 5 or something like that. Go ahead and get in there and label those. So now, that's another thing. This is not an XY scatter chart. It looks like one. Okay, this is a line chart. So when you go to make that chart, select line chart, because a line chart has categories on the x-axis, not data. So we don't have data points like y versus x. We have y versus date. It could be any category. It could be color. It could be text of any sort. You can just have some kind of name and the data point associated with it, and then it would put all of those names along the x-axis. Like I could do grades and the thing. Your names could be along the bottom axis and your grades here. So it's data versus category. Okay, so that's what a line chart does. And you still have the markers and lines and so on like you have in a scatter chart, an XY scatter chart, but the x-axis is categories. So you'd want to go in then and make sure the x-axis is date, is a category of date, and it selects your date column. Sometimes it just puts numbers there, and it's data point number, okay, instead of the date. Now you can go in and figure out how to skip certain days. Like I've set it to where it skips 7 days, and so these are the Mondays. So that kind of keeps the x-axis clean. So I have it skip 6 days or 7 days, and so it shows up with all the Monday dates. And you want them rotated 90 degrees so they don't crash into each other. So I can look at it and see the dates on the side. Okay. So let's do a top hat. All right, so in our control charts, what is the pull? I'm going to start the timer so we can stay on track. Okay. It's just multiple choice. Punch the button. Okay, so let's see how everybody thought. Very good. It's the data outside the action limit, and that word action limit's giving it away, isn't it? Okay, so whatever thing causes you to take action, that's the pull. Okay, the Kanban, in the past, the pull and the Kanban were synonymous. So if whatever we're using as the signal to take action was called the Kanban, but it seems like now that language is shifting to where the Kanban is more like the dashboard too. So you could make an argument that our whole control chart is the Kanban, but still the pull is our action limit. So when it goes above the action limit, that's the pull indicator. But Kanban's getting a more broad use as a sort of a dashboard. And our control chart would be like a dashboard of our system. You could look at it and see how stable it's been over the several days or weeks or months. Okay. But the pull is the key, and that's when the data point jumps above our action limit or below it, then we take action. Okay, so what's wrong with this control chart? Yes?
The data points are more, I guess, scattered in between data.
Yeah. So this is so this is not what we mean by continuously variable data. So we really have four answers here, four categories. And so this is now flow rate. I mean, the idea of flow rate is continuously variable, right? It could be any kind of liters per minute, but whatever system we're using to measure it has got a problem, and it's only reporting out, +1, 0, -1, and -2. So it's almost like a rounding error or a digitization error. So it's not that flow rate is somehow categorical. It's our measurement system. So this is a problem with our measurement system. It's not producing continuously variable data. So you need to look at the data itself to see if it's continuously variable. It's like gas prices. You can have any price of gas, but it doesn't change very often. And so you see, it's the same several days in a row, and then it jumps up 10 cents. And then it's the same for several days in a row, and jumps back down. So you end up a lot of times with gas prices getting categorical data, even though the concept of gas price is not categorical. You don't go in and buy gas and they say, okay, we'll charge you the high price today. We'll charge you the low price. Like categories high and low. In theory, it's continuously variable, but it doesn't behave that way sometimes. Sometimes it produces categorical jumps. Okay. And that's what this data is doing. And the reason it is not good for process control is it's not statistical. It's not, right? These points are not out of control. So you're not getting good statistics. It's not a statistical probability. 1/4 of the data points, since you only have four categories, are going to be in this group. And so you're going to be out of control 25% of the time, not less than 5% of the time, which would be normal for being outside of the 2 sigma limit. Okay, obviously, what's wrong with this chart? Trending, yeah, that's right. That's temperature. It says flow rate, but it's really temperature data. It's like just in the spring, it's warmer and warmer, we hope, right? Okay, now let's look at some of these control charts. So I love these things. Man, don't have me check temperature daily. That's just so boring. Why would I, can we get a machine to do this? And the answer is yes. Okay. And not only that, but the machine can record itself. And so this is relative humidity. And they typically have relative humidity and temperature. So like one of these might be temperature, one of these might be relative humidity. Okay. And you start it and they cruise along, and it's got these crazy patterns on here. That's graph paper. And there's tiny little numbers right here. Like, see, this says 30% right there. This says 40, 50, 60. So we follow that little wheel around, and it's hovering right around 30%. So if you're working with a process that has to have low humidity, you could buy one of these and track your humidity. And if it went on an excursion overnight and then came back down and controlled during the day, you would know it because you'd come in the morning and you'd see this excursion of humidity. Why is that important? Well, maybe your samples absorb water. And you had your samples in the tray and everything was fine. You left for the day. AC went off at night because something happened, power outage, came back on at 4 in the morning. cooled everything back down, dried everything back out. You come in thinking everything's fine, but overnight the room got really humid and your samples are now heavier and they got water in them. And so that's a problem. Now, this one's $960. Now I know it's sometimes for academics, students and professors, we're like, man, that's expensive, right? Just the 2 little ink pens and a piece of paper, $960. Okay, so let's have you measure temperature every hour. Okay, how long does that take? A few minutes. Let's say it takes 5 minutes. So in an 8-hour day, 5, 10, it's a 40 minutes. Let's round up to an hour. Let's say it takes 1 hour of your time to monitor the temperature on your shift. What's the hourly rate? Let's y'all pick one. What do you think? 22? Oh, wow. Okay. That's good. Okay. And so times 1 hour per day. And then we're going to take, so then we're going to take this number here, and we're going to divide 960 by that number. All right, so somebody divide 960 by $22. 43.6. Okay, we round up to 44 days. So you're going to break even at 44 days. If it took a person an hour to monitor temperature, cumulatively over a whole day. Okay, and to make decent wages. Okay, so this isn't that expensive. That's the point, Here's an electronic one. I mean, so you got to buy paper, right? And you got to, this process still requires a little maintenance, and then you got to pay attention to it. You can't just let it sit in the corner. Here's an electronic one, plugged into the computer system. I couldn't find a price for this one, but anyway, you plug this into your system, and it tracks the data and can alert you electronically. Now, in the future, they call it Industry 4.0. I don't know what 1, 2, and 3.0 were, but 4.0 is where these kinds of control apparatuses actually control parts of the process so that it's dynamic. And so in cleaning, in the area that I work, they're talking about monitoring the solvent or say the surfactant in a cleaning bath. And when it gets low, that raises a pull indicator, and then I've got to add in some more soap or pull the grease off the top or what have you. And Industry 4.0 would be computerized dosing, computerized maintenance of the system. So the computer sends up a pull signal, and then that pull signal creates another computerized module, and everything is monitored from the front. Okay. So that's our little module on statistical process control. So you should be working on your control charts and start uploading those to those links. All right, y'all have a good day.